For our second speaker, it's a great pleasure to welcome a distinguished visitor from the United States, Dr. Alan Stern from Southwestern Research. I just remind you that we awarded Alan Honorary Fellowship in 2015 for his distinguished body of work in planetary science and also for his leadership at a very senior level in NASA. Anyway, Alan is going to talk to us now on the exploration of Pluto by NASA's New Horizons mission.
Well, I want to say thanks for that introduction, but also thank you for the very great honor of being invited here. It's a pleasure to come and give this presentation, and I'm looking forward to the conversations afterward over drinks and dinner. And I should say that I really enjoyed the beginning of Professor Owen's presentation when he spoke about his meeting with Professor Dungy and the first problem that they tackled. Because as an undergraduate, I published a paper called On an Optimal Speed for Traversing a Constant Rain in the American Journal of Physics in 1981. And in fact, it's also a mathematical paper, and if you decompose a finite elements model of a person into the horizontal and vertical cross-sections and solve for the optimal speed, you'll find that you got the right answer.
Yeah, well, so this was 1982, so you might have been the inspiration for this.
Well, I don't know about that. But what I want to do is give both a scientific and a kind of exploration lecture, telling you about how this project came to be, what the scientific motivation for it was, and some of the chief results that we've obtained in the last year since all the data has reached the Earth. And I want to start with this candid picture that was taken on the morning when the first high-resolution image was first displayed within the science team room, a room about this size. Those are members of my science team in July of 2015 reacting pretty emotionally to that first image of Pluto at close range. And I wanted to put this picture up particularly because for us, like many of you who've worked on long-term projects, and this one took a quarter century, it was quite an emotional event to see it culminate in a complete success. And I also wanted to put the image up because as principal investigator, I think I get a little bit too much credit. In fact, probably a lot too much credit. 2,500 men and women worked to make this project come to fruition. Most of them engineers and technicians who designed and built the spacecraft and the launch vehicle, but quite a number of scientists, almost 200, and many other professional skill sets. So I'm here to represent them. I often like to say that the real acronym behind PI isn't principal investigator, it's the principal instigator, because everyone else does the real work. Well, this is the planet Pluto, seen in true color by New Horizons on the Encounter hemisphere that we flew past on the morning of the 14th of July, 2015, culminating a 9.5-year flight across the entirety of our solar system. This is a scale bar showing the diameter of Pluto, and I think you can see by just casually looking at the planet, in each quadrant you'll find completely different geology. It is a spectacular scientific wonderland, and I have a lot of things to tell you about what we found. But I have to tell you, for those of us who sold the mission, we expected to find something complex. We expected to find something dynamic, but even for us, this exceeded our wildest scientific expectations. I'll say a lot more about the scientific results after I give you background on the project. I want to start at the very beginning, the beginning of the 20th century, with this scientist, Percival Lowell, who founded Lowell Observatory and who became convinced from the apparent astrometric residuals of Neptune and Uranus's motion that there was another planet creating a systematic effect on their orbits. And he launched, with his own funding, a search in the very first years of the 20th century for that so-called Planet X. Lowell died in 1916, having never found his Planet X, but he left his observatory and very much of his fortune to continue that search. In the late 1920s, the observatory hired this young man, Clyde Tombaugh, to come and take over the search. Tombaugh, I believe, is today, unfortunately, vastly underappreciated. He succeeded at what half a dozen others had tried in the previous 25 years. He found Lowell's Planet X. He did it without making a single mistake, without ever having a false alarm. He did it by reinventing the entire search technique, collecting all the data himself, reducing all of the data, and doing all of the data analysis. And what he actually found, of course, was the biggest and the brightest, and of course the first discovered member of the Kuiper belt. The second member of the Kuiper belt was not discovered until the 1990s. And I think that's a testament to how far ahead of his time Tombaugh was. Now, I got to know him a little bit early in my career, just before his death in the 1990s. These are very small snippets out of the glass plates in the constellation Gemini, where Pluto was discovered in 1930 by Tombaugh. And his data analysis technique was to take images on successive evenings and look for the motion, the slow motion of the planet he was searching for against the fixed stars and against a blizzard of foreground moving targets like asteroids. And he did that with what was called a blink comparator, in which you put two images into a kind of a microscope, and you switch between them successively, looking for something that's jumping at just the right rate to indicate it's orbiting beyond Neptune's distance. Now, Tombaugh, I think I can use this pointer. Tombaugh always said it really wasn't all that hard because Pluto's always the one with the arrow. But searches took place after his discovery of Pluto for more objects in the distant solar system, across the 30s and 40s and across the 50s, 60s, 70s, and 80s. And as I said a little earlier, it was only in the early 1990s, with the development of CCD detectors and what were then fast computers for data analysis, that the first slow-moving target in the Kuiper belt was ever discovered. Now, I actually will take the liberty of showing this table from a National Geographic issue that was published when I was a boy. And I'm sure that virtually everyone in this room at some point saw a diagram of the solar system that looked like this in your youth, and a table with the facts about the planets that were then known that looked something like this. And the important systematic, the planets are arranged in that table in order of heliocentric distance from Mercury outward to Pluto, and you don't have to be able to squint very hard to see that the numbers to the left transition to increasing numbers of question marks as you move to the right. Because, of course, in planetary science, we deal with the very difficult problem of reflection, which means that signals grow fainter by r to the fourth. And so for the outer solar system, it really was a terra incognita for a very long time. And it's only through the development of spaceflight and being able to actually go to these places that we've been able to really understand the magnificent worlds that were formed 4.5 billion years ago, so far from the sun. Now, in the case of Pluto, primarily beginning in the 1970s and continuing in the 80s, we were able to make progress. CCD detectors, advances in infrared astronomy, and other techniques allowed us to learn a number of things that really were quite fascinating. At the top of this chart is an infrared reflectance spectrum of Pluto made in the early 1990s, showing strong absorptions due to molecular condensates on its surface. The methane, the CH4, which makes the biggest absorption features here, is actually present in the lowest abundance. But because it has a large cross-section for the interaction with infrared light, it makes the biggest absorptions. Carbon monoxide, much tougher to find, much weaker features, is also there and about an order of magnitude more abundant than the methane. But it's the nitrogen, which you can just barely see by this kink in the spectrum at 2.15 microns, that is actually the dominant surface constituent. The discovery of the nitrogen really changed our ideas about Pluto's surface in many ways, and I'll come back to that a little bit later. But from this kind of work, it was known, even 25 years ago, that the surface of Pluto had 3 different active volatiles that at the relevant temperature on that surface, it could all be mobile. So whereas on the Earth, we have 1 active volatile, H2O, and on Mars, we have H2O and carbon dioxide. On Pluto, we have an even more complex situation, which also suggested that Pluto might have an atmosphere, because you can calculate the expected vapor pressure in thermal equilibrium with the radiation field at the surface and predict an atmosphere that's about like the pressures in the Earth's mesosphere, 80 kilometers overhead. Some number to perhaps some tens of microbars. And so a search was on, beginning in the late 1980s, to actually detect the signature of that atmosphere. The easiest way to do that is with stellar occultations, which are rare because Pluto's cross-section of the sky is very small. So stars don't occult it very often. In fact, it's only about 100 milliarc seconds in diameter as seen from the Earth. That's primarily due to its range, 5 billion kilometers. But in fact, the Kuiper Airborne Observatory, along with several ground-based telescopes, detected this signature of refraction in a stellar occultation in 1988. And that occultation result is shown here. This is the combined light level at the top of the star plus the planet. And then you'll see that the light level drops over a period of several tens of seconds, which is the distinct signature of refraction. Had there been no detectable atmosphere, we would have seen a knife edge and then diffraction spikes, and that's it. This is the signal level with the star missing, and then it rises again. This trace not only gave us the fact of the detection of an atmosphere, but it gave us a good handle on the mean molecular weight, some indication of the temperature in the atmosphere, the clear signature of atmospheric vertical structure. You can see a steeper profile near the bottom of the trace than these gentler slopes at the top, and a number of other enticing attributes that opened the study of Pluto's atmosphere. We had pretty good evidence back in the 1980s because Pluto's largest satellite, Charon, had been discovered, and it's half Pluto's diameter, that in fact that system had so much specific angular momentum that it could have only been formed by a glancing blow by a protoplanet onto Pluto in much the same way that a giant impact formed the Earth-Moon system. And then, very much to our surprise, when we first determined a crude handle on Pluto's diameter and could measure its mass by the barocentric wobble of Pluto and Charon, it was determined that although the surface is made of these extreme ices, that it is in fact not an icy body by mass. Pluto is in fact almost 70% rock. Its density is about 2 grams per cubic centimeter. This is a cartoonish model of what the interior might look like prior to New Horizons. A thin veneer of these extreme volatiles on the surface, water ice for the mantle, and then a very large rocky core. And that's the satellite model, which has somewhat lower density. So these facts told us that Pluto was going to be a pretty interesting place. But unfortunately, because of its distance, we were not able to resolve its surface. I hear the snickers. I was the principal investigator of this Hubble Space Telescope program that made the first resolved image of Pluto. This, in fact, was the best image of Pluto's surface ever made before New Horizons. And you can't learn very much from this. Now, I will admit that we published several papers on this. And I understand there are quite a number of extragalactic astronomers and cosmologists in the audience, so you'll understand how working with meager data sets, and one might be tempted to speculate. Can you see the northern polar cap? Well, in planetary science, the great lesson of exploration has been, ever since the first missions to Venus and Mars, in which we were so surprised by what being there could teach us about the detail that we could not see from afar, even for those planets that are 30 and 50 times closer than Pluto, you really can't learn very much from images like this. This is the kind of imagery that you need to understand a planet. And from imagery like this, if this was the only image we had of a given planet, this one, Earth, you could deduce quite a bit. I asked one of my postdocs, Amanda Zangari, when she came from MIT and started work, her very first assignment on day one, I asked her to pixelate this image to the Hubble resolution at Pluto. And this is what you get. Now, as a scientist, what could you determine about the Earth at this resolution? Very little. I would challenge you to even conclude that there are continents and oceans. And I will drive that point home farther. Now, you probably think you know what you're looking at. I'd like you to tell me if you're right. It's not Mars. It's really resolution that matters, and that's why we send spacecraft to the planets. That and the ability to do in situ work for magnetic fields or mass spectroscopy or what have you. All of you probably remember the Voyager program that NASA flew in the 1970s and 80s to explore the giant planets of our solar system. When Voyager was launched, there were 2 spacecraft, both to Jupiter and Saturn, and then they had an option of directing the first one onto Pluto, while the second one went to Uranus and Neptune. But along the way, they concluded that a safer bet was to make a more thorough exploration of the Saturn system. And so they elected not to fly to Pluto, and instead to explore Saturn's fascinating and giant planet-sized moon called Titan. And that sort of foreclosed people's minds that we would ever fly to Pluto. But in 1989, when Voyager made its last flyby exploration at Neptune at 30 astronomical units, I was just finishing graduate school, and along with a number of young professors and graduate students and postdocs like myself, we really started to ask, well, why not send a mission to Pluto? Why not, given all of the fascinating things we know about its interior, its atmosphere, and its surface, go to this different type of world farther still? Well, I don't think we knew what we were getting into, because it took us over a decade, in fact, 14 years, to find the right combination of spacecraft design and management institutions, and the right case to be made to unlock the funding. This is basically a billion-dollar enterprise. The cost of New Horizons from inception to the culmination of its prime mission at Pluto was in fact about $728 million. And that leaves aside several $100 million that were spent on studies of how to do Pluto missions before New Horizons was born. All of these Pluto missions that you see from Voyager that could have gone there across all of these concepts never made it off the drawing board until New Horizons. It's the only one in which we actually built something. And I want to say it was a very difficult job in the United States, in NASA, for each of the primary scientific disciplines like astrophysics and heliophysics, earth science, and planetary science. We choose our priorities through a National Academy process called the Decadal Survey. And in planetary science, there are typically 50 to 100 proposals, when in reality only the top 2 or perhaps 4 will be fundable. So there's a very steep gradient between good ideas and those that reach consensus that they are so important that they should receive funding from the limited budgets that we have. Now, how did the exploration of Pluto reach that point? it began with our old understanding of the architecture of our solar system. This is a diagram which I suspect all of you also saw when you were very young, with a 20th century view of our planetary system. You see the classical grand design architecture that we all learned to love back then. And the inside are 4 rocky terrestrial planets surrounded by a debris belt called the asteroid belt. Then somewhat farther out are 4 massive giant planets, completely unlike the terrestrials and at orbital distances that are from 5 to 30 times farther out. And then Pluto in an unusually elliptical and inclined orbit and with a very small mass by comparison to either the terrestrial planets or the giant planets, and orbiting alone and not fitting either pattern. Well, that 20th century view was organized and universally accepted, but it turned out to be completely wrong, both in its understanding of the architecture of our planetary system and in our understanding of its content. Because in the early 1990s, the Kuiper belt was discovered, the context for Pluto. And Gary, I hope that you can start this video for me because I don't have a way to do it. This is a view looking down on the orbits. Well, not that one. Let's go back. That one. There we go. And we can turn the sound down, please. The dots that are appearing are discoveries of KBOs, Kuiper belt objects, as a function of time. 1992, the first, 4 more in 93, 10 in 1994, and now there are literally thousands. The larger dots there are actually Pluto-sized objects. In a moment, this nice graphic will rotate to show a 3-dimensional view of this disk, which is in fact the 3rd zone of our planetary system, beyond the terrestrial planets and the giant planets. This revolutionized my field. I thought the solar system, the outer solar system, which I call the giant planets, that turns out to be the middle zone. It's the largest structure in the planetary system. And perhaps most importantly, beyond revolutionizing our knowledge of the architecture of the system, there we go, we discovered this new class of objects, the dwarf planets, that outnumber the terrestrial planets and the giant planets combined. In fact, this 3rd class of planets, of which Pluto is the largest and of course the first discovered, actually dominate the census of planets in our solar system. And they have all the attributes of planets. And unlike the astronomical community, my community, the planetary science community, is not afraid of large numbers of planets. We don't worry about school children and whether they can memorize all their names, any more than one would expect school children to memorize all the names of all the elements in the periodic table. So this has really been a revolution in our field. The discovery of the Kuiper belt and the discovery that the solar system primarily made dwarf planets really shook the field to its roots and is today still reverberating as a massive discovery from the 1990s. I want to show you where Pluto lies in the pantheon of planets in our solar system, for it's not the smallest body. It's about in the middle of the distribution. All of these objects are in hydrostatic equilibrium, which is what makes them round and look like you would expect a planet to look. It was that discovery, the discovery of the Kuiper belt and the large population of dwarf planets in the 1990s, that argued so strongly for our National Academy in 2003 in that decadal survey to raise the priority of a mission to Pluto, because it had transformed from a fascinating place that we had not visited to the archetype for a whole new class of small planets in the solar system. So that by studying Pluto, we could, by extension, begin the study of this new class of object. So, in fact, what was called the Pluto Kuiper Belt mission rose to the #1 priority for a new start as a result of that decadal survey, and NASA conducted a competition. There were 5 industrial teams that formed. If you work with ESA, you know what this is like in getting a medium-sized or cornerstone mission. This is a large enterprise in and of itself. I led one of those teams called New Horizons, and we were fortunate enough to win that winnowing process in 2001. That's the cover to our proposal, the lower right. And then we spent 4 years working nights and weekends. It was really quite an enterprise. I said that 2,500 people were involved. I have to put this to scale. If you know the missions like Cassini and Galileo and Voyager, you probably also know that all of those projects had 10 to 12 years to design, build, and test their spacecraft. Unfortunately, by the time we had a decadal survey select the mission priority and then a NASA competition, there was only one remaining launch window in the 2000s. And it was only 4 years and 2 months after we were selected. So we basically had to create an outer planets mission in a little less than half the time it had ever been done before, including the scientific instruments, the whole kit and caboodle. And I will say, for the people that worked on New Horizons, it really became a labor of love. And I know that there are many similar projects. James Webb has been going through that for a decade now, and LIGO went through that. But the people who worked on New Horizons, I am in unending awe of their ability not only to work, but to produce a product of unheralded engineering reliability. This was the first planetary mission ever designed from scratch to fly alone, not as one of a pair, but to fly alone, and on the longest journey. And yet, they made it work. Now, there's a whole story behind this, and this is an unabashed advertisement. My colleague David Grinspoon and I have just written a book called Chasing New Horizons. It's the entire story of the project, which I will not tell here. But you can go to Amazon now and buy pre-publication copies. It will be published on the 1st of May, and that's the cover. Now, this is the spacecraft that we built. I just want to give you a little bit of insight. There's a dish antenna at the top. You can see how small it is because the humans represent the scale bars in this. It is very tiny compared to Voyager. It weighs about a third of what Voyager weighs, and it's sent on a very similar mission, but with a much higher power payload. The spacecraft is nuclear powered. The nuclear power generator, fueled by plutonium, is here. There's a 2-meter dish antenna that operates at X-band for transmitting signals and receiving commands from the ground. Inside the spacecraft bus is the propulsion, the guidance, the thermal control, the command and data handling, all the systems. And the scientific instruments are mounted on the outside. In fact, these two, Professor Owen, are plasma instruments, SWAP and Pepsi, that are respectively spectrometers at KeV and MeV energies. The primary optical instruments are unfortunately on the far side of the image I just showed you. But in total, there are 7 scientific investigations on board. 2 plasma instruments to study pickup ions coming off of Pluto's atmosphere to understand its composition, and an instrument called SWAP, whose job was to measure the escape rate of the atmosphere. The primary remote sensing instruments on board are an infrared mapping spectrometer for composition that can simultaneously develop 64,000 spectra at one time. So you can blanket the target with pixels and get a spectrum at every location. An ultraviolet mapping spectrometer with 32K pixels for understanding the atmospheric temperature pressure profile and composition. And a long range or long focal length panchromatic camera called LORRI, whose job was to make the highest resolution images and let us start very far from Pluto in surpassing Hubble resolution. Additionally, there's a dust counter on board to study the heliospheric environment, and there's an instrument called REX, which is radio science, with a number of jobs measuring brightness temperatures, radar reflectivity, masses by Doppler shift, and perhaps most importantly, the temperature pressure profile in the lower atmosphere through a radio occultation technique. 7 scientific instruments. In order to travel quickly across the solar system, we built a very small spacecraft, and we put it atop the largest launch vehicle in the U.S. inventory at the time. This launch vehicle, which is about 70 meters tall, is called an Atlas V. We bought the most powerful variant of the Atlas V. But the spacecraft that we put on top, which is maybe twice the size of this podium, was essentially like launching an Atlas V empty. It's built to launch things larger than the Hubble. And here we put this little hood ornament up on top. and then launched it in January of 2006 during that last launch window to Pluto. Before we launched it, we did one thing that we had been asked to do in the 1990s when I was chair of the study groups for early Pluto missions. Clyde Tombaugh had asked, if you ever really get a mission to Pluto, I'm going to leave my ashes with my family. Could you have some of them put aboard the spacecraft? And we did that. And I believe he's the first human being to ever be, whose ashes have ever been launched on a planetary mission. And then, as I said, we launched. It was the 19th of January, 2006. I have a video of the launch, and I'll get Gary's help with that, getting it started. And we can turn the sound down,
Go Atlas.
because you don't need to hear the announcer.
This is
I'll tell you
Atlas
about
Launch
this. So
Control
the
at T
Atlas,
minus 10, 9,
which weighs several
8,
million pounds,
7,
normally
6,
lifts off at about
5,
3/10 of a G.
4,
Because we
3,
had this
2, 1. We have ignition and liftoff of NASA's New Horizons spacecraft on a decade-long voyage to visit the planet Pluto and then beyond. That's 15 seconds. Everything continues to look good as the Atlas V vehicle climbs away from Florida's east coast. The 5 solid rocket strap-on boosters are burning just fine, sending the New Horizons spacecraft on its way to the very edge of our solar system.
And then, of course, they're discarded efficiently. You'll see them on the stage in just a moment. They separate the two ways so to make sure that we have a collision. Then the sustainer engines burning kerosene and liquid oxygen continue to fire for another couple of minutes. There's the separation. Before the sustainer stage completes, we're actually at altitudes that are high enough, about 100 kilometers. And very quickly, we can discard this have to go that way either. So very far out. The horizons is out there exposed to the space environment, being accelerated at about 4 Gs by this very large rocket. First stage finished. Second stage, a Centaur liquid hydrogen, liquid oxygen stage, put us in Earth orbit. And then we flew around over Saudi Arabia, where the injection point was to fly to Jupiter for a gravity assist, and lit the second stage again to take us out of Earth orbit, and then a third stage, a solid rocket motor, put us on the trajectory to Jupiter. And in that process, New Horizons became the fastest spacecraft ever launched. In fact, we passed the orbit of the moon 9 hours after launch, which for scale is 1 order of magnitude more quickly than Apollo missions. This is a cartoon view of our route of flight from launch in January of 2006 to Jupiter flyby 13 months later in February of 2007, and then a very long voyage across 2.5 billion kilometers of the middle solar system to reach Pluto. Pluto's orbit is shown there in yellow, and you'll notice that we were able to intercept it just as it crossed the invariable plane of the solar system, which is very important energetically, so that we didn't have to sacrifice energy from the launch vehicle to change plane. We could instead put it all into forward speed, which allowed us to make this crossing in only 9.5 years. By comparison, the Voyager 2 went to Neptune, took 12 years, and it had the advantage of 4 gravity assists to get there. We had a gravity assist from Jupiter, which added about 5,000 meters per second to our speed in February of 2007. But primarily it was the launch vehicle that did the job. Now, Jupiter is the only thing we passed along the way, and so we used it as a very intensive flight test for all the software and for the instruments on board. This is the cover of Science from later in 2007, showing a couple of images from New Horizons of Jupiter itself and of Io, the volcanic satellite, the innermost of the Galileans. If you look very carefully, I'll take the laser away, you could see a little something blue up at the top. That's actually true color volcanic plume, which we studied with time-lapse photography on board. In fact, we conducted 700 scientific observations in the Jupiter system, studied the magnetotail by flying right down it to several hundred RJ, studied all of the satellites, the large satellites, Jupiter's ring, and its meteorology. and over 100 papers have been published. I don't have time to go into that, and I don't believe this video will work. But we spent the next 8 years flying across that great expanse of space to Pluto. And I just want to say, although it took 2,500 human beings to design and build the flight system, in flight, we pioneered a technique called spacecraft hibernation, in which the spacecraft takes care of itself with an onboard autonomous agent, software, if you will, for fault detection and correction, that allowed us to operate the spacecraft on a very small team. Voyager had a team of 450 people in flight. New Horizons, a little less than 50. That's the science team, the operations team, the engineering team, and a couple of people to manage the project. All of it. So that's probably half the number of people that are in this room. An order of magnitude less people, and we saved hundreds of millions of dollars by doing that. And it's the first extensive use of hibernation in the history of the U.S. planetary program. And I want to say that one of our challenges in getting to Pluto was navigating there. Of course, we knew basically where Pluto is, but because it hadn't completed an entire orbit and closed the loop, if you will, on the astrometry, there was a considerable astrometric uncertainty in Pluto's position, which we ultimately had to take out as we approached the planet in 2015, using our onboard imagers to make careful images against the star fields and ship them back to the Earth. In fact, over 1,000 of those images, so that we could measure Pluto's motion against the star field and through parallax, essentially, by solving a big system of equations on a bunch of stars and one dot called Pluto, solve for the range to the target, and difference that from where we estimated the spacecraft was through radiometric tracking and other techniques, and then use the differential to compute engine maneuvers to correct back to course over and over, basically to home in by remote control from 3 billion miles away, so that we could take out all those errors in the orbit uncertainty. And our goal was to fly through the shadows, as shown there, the red trajectory moving from lower right to upper left, to fly through the occultation shadows of Pluto and Charon. In order to do that, we had to hit a closest approach aim point measuring 40 by 60 kilometers, which is a pretty big space if it was towering above London, but from 5 billion kilometers away, it's a pretty small target. We also had to arrive within 9 minutes of the expected time, because although the spacecraft has a lot of scientific capability and a fair degree of smarts in how to operate itself, it actually can't look at its own data. So it can't tell if a target is centered in the field of view. So we pre-compute that, and we tell the spacecraft where to point in right ascension and declination for every image. In order to do that, you have to not only know where Pluto is, but where all the satellites are, where your spacecraft is, and that means you have to know the time at which your arrival is occurring, because everything's moving, and the last thing you want are blank images, or maybe embarrassing images that clip the limb of the planet. That 9-minute arrival window was essentially unheralded in the technology that people had used in the past for planetary missions. And we hit it. We actually arrived 86 seconds off target after the 9.5 years. And so now I'm going to turn to the Pluto system. This is a kind of a family portrait. If you're not familiar with Pluto, it has a very large satellite, half its own diameter, called Charon, which you see to the upper left. And then it has 4 small satellites orbiting beyond that pair, which actually constitute a binary planet because their barycenter is in free space between them. And this is a true color family portrait, although only 2 of the 4 small satellites are shown. I'll say a little bit about what we learned about the 4 small satellites. They're all irregular icy objects. We have infrared reflectance spectroscopy that shows they're made of water ice. They have normal reflectivities of 70 to 90%. How their surfaces stay so reflective after the constant rain of dust from the Kuiper belt, we do not understand. All of their rotation states are excited. They tumble in obliquity, and they spin very fast compared to their orbital rotation periods. It was expected they would all be tidally spun down, because the tidal spin down times can be computed, and for any reasonable assumption, they're very short compared to the age of the solar system. Hydra, the largest and most distant, actually rotates about 100 times, more precisely 90 times, for every Kepler orbit it makes around the binary. And this was a surprise. What is exciting the system dynamically has not yet been proven, but it's very likely to be the asymmetric force field of the binary rapidly rotating below it. But it's created some very interesting dynamics. I won't say more about the small satellites. I'll say a little bit about the big one, Charon, which has a diameter of about 1,200 kilometers. It's very reminiscent of a typical icy satellite of Jupiter or Saturn or Uranus. North is up in this image. I think the most predominant things that you'll notice are that there are a large number of craters. In fact, when we look at the density of craters as a function of location on the surface, we find that it's about the same everywhere, meaning that all the surfaces are of roughly co-equal age, which we can invert with models of the cratering population, and we retrieve an age of about 4.5 billion years. So this object is as old as the solar system, or more or less. You'll notice the very large extensional tectonic belt across the equator. That almost certainly was caused by these extensional forces due to the expansion of liquid water as it froze in the interior after the formation of this world. If you look closely at the crater blankets, the ejecta blankets around this object, you'll notice that some have very bright ejecta and some have dark ejecta, and there doesn't seem to be any pattern that we can find with latitude or longitude or geographic province or depth of the crater. This may be telling us about inhomogeneities below the surface, or it may be telling us there are two populations of impactors, that some are brighter and some are darker. Frankly, Charon, although a fascinating object, pales compared to Pluto in our scientific interest. So I won't spend more time on it, except to tell one very interesting scientific story, and that's about this polar feature, the stain at the North Pole, which is actually red. This is a color exaggerated image, but only slightly so. Really in the history of the study of icy satellites from Jupiter outward, we had not seen anything like this. And in the case of Pluto, we think we understand what's caused it. I'll show you some more details about Pluto's atmosphere in just a few minutes, but that atmosphere is escaping to space, and the primary escaping constituent is methane. Although methane is a trace species on the surface in the atmosphere, it's the lightest of the main species, and so in Jean's escape, it's going to win. It's going to have the highest escape flux. It's about 10 to the 25 methanes per second, flowing outward roughly symmetrically. Charon presents a barrier to some of that methane. It has a solid angle that's about 40 times the way that the Earth's moon appears in our sky. Although it's smaller than Earth's moon, it's much closer to Pluto, only 20,000 kilometers away. It intercepts that methane, and at the poles where it's coldest, only 20 Kelvin, the methane cold traps. And unlike near the equatorial regions where it can then resublimate and hop around on the surface until it's photoionized or lost by some other process, at the poles, it's just going to sit there in the radiation bath of solar ultraviolet. And we've actually taken a cold finger in a laboratory at NASA Ames Research Center, cold finger at that temperature, 20 Kelvin, put the methane there with a solar simulator lamp, and produced precisely this color, and for that matter, the spectrum of this material that New Horizons retrieved. This is what's called a tholin, or a chemical byproduct by ultraviolet processing of methane. And so we think we have a pretty good theory for what's going on. It's actually material from Pluto's atmosphere that's accreted and then been chemically transformed by this radiation. If the theory's right, then the South Pole should have a similar feature, but we can't see the South Pole because it's in winter polar shadow. In about 30 years, it'll emerge into sunlight, and I'm sure we'll write another paper. This is the binary pair itself, and I use this to illustrate the great dichotomy between Pluto and Charon. Pluto is much brighter, much more colorful, much more active than Charon, despite the fact that they have coexisted in the same bombardment environment, same thermal environment, same radiation environment for billions of years. there's a great difference between nature and nurture, and this proves it. This is one of my favorite images of Pluto because it shows the atmosphere and many interesting features on the surface. It was taken just 15 minutes after closest approach, looking backward in forward scattered sunlight, which allows us to see the well-organized haze layers above the surface. And you can also see how rugged the surface is in terms of topography. For the entire decade that we flew New Horizons across the solar system, my science team debated whether we would see steep topography on Pluto's surface, because the nitrogen ice that dominates the surface composition is mechanically weak. You can make it in a laboratory, and it has a viscosity about like room temperature toothpaste. Try to build a mountain out of room temperature toothpaste. Even in Pluto's weak gravity field, it will slump, it will relax. The Maxwell relaxation times for steep topography on Pluto, if made purely of the nitrogen, are short. They're like 1/1000th the age of the solar system. So we had a debate. If the surface had a deep layer of nitrogen, we hypothesized we would not see steep topography because it can't support it. And if we saw steep topography, that would probably tell us that something was underlying a veneer of nitrogen that was in fact mechanically strong, probably water ice because it's the dominant constructional material in the outer solar system. And that's in fact what we see, steep topography. So it must be the case that the nitrogen is a veneer on the surface and that something else is supporting it. Later, we got compositional information to tell us that we could see water ice outcrops in many places in the mountains. And so we confirmed this theory. Now, this is another image. It's actually a mosaic of images in stretched color to accentuate the great differences across Pluto's surface and wrapped onto a sphere. So it's sort of a dramatic representation of what the place really looks like. There's a lot of complexity going on here, but the primary feature I want you to focus on is this large nitrogen ice field with a surface area of about 1 million square kilometers, which we've named Sputnik Planitia. It is a plain, about 1,000 kilometers north to south, below these mountains that ring it, 3 to 5 kilometers above the plain, made almost entirely of molecular nitrogen. I'll show you higher resolution images of it shortly. We believe it's an impact basin that became a cold trap to the nitrogen on Pluto's surface and became, therefore, the dominant reservoir of nitrogen on Pluto. No feature like this, and if you're familiar with Pluto having a heart on its surface, Sputnik Planitia is the western lobe of this heart. The heart has been named Tombaugh Regio for Clyde Tombaugh, but this western lobe is this vast glacier. The eastern lobe has a veneer of nitrogen over mountains. I'm going to concentrate on Sputnik. This is a higher resolution image made by New Horizons by our LORRI camera, which again is panchromatic, so I don't have a color to show you this. This is in the northwest quadrant of Sputnik, where the glacier abuts these mountain ranges made of strong water ice, mechanically strong water ice. These are the mountains. And where there are obstacles to the glacier, you can see flow patterns. So there are dynamics taking place here at 40 Kelvin in this molecular nitrogen that are directly reminiscent of the kind of glacial dynamics that we see on Mars and that we see in places like Greenland and Alaska here on the Earth. And I will tell you, it's hard to tell you what a surprise this was, but let me illustrate it by the fact that when I selected this winning team of geologists and atmospheric scientists and geophysicists that is the New Horizons science team, I didn't have a single glaciologist on the team because we didn't expect glaciers on Pluto. And yet the largest, most prominent feature on the surface of Pluto is in fact the largest glacier off the Earth in the entire solar system, and it's dynamic. And we see other evidence of its dynamics. Here, where the color code is altitude that has been retrieved from stereo imaging from different angles as we did the flyby, we can see in this chute in the mountains several kilometers above the surface of Sputnik, where the nitrogen has poured down through a valley, perhaps in an avalanche or some other energy release mechanism, and pooled out on the surface. And if you look at this pool or at the rest of the glacier, you'll notice it's young. It's young, we know, because we can't find craters on the surface. And the craters are the proxy for the age. So in the recent geological past, we see evidence for flows, for avalanches, and yet in other places on the planet, we find saturation cratering. So places that are very old as Charon's surface, 4.5 billion years old, such as this location here in the western lobe of Sputnik, just against those mountains. Here's the mountains, so west is to the bottom here, west is to the left here, sorry about that. And this is the margin, the contact with the glacier, Sputnik. When we look right in the heart of the glacier, we find this interesting geophysical cellular pattern that repeats itself across this vast expanse. We believe it's caused by convection in the ice, and we have published several papers, including one on the cover of Nature, with models supporting this. Now, what the heat source is below the ice that's causing this convection to take place, a Rayleigh-Taylor instability, is unknown. There are quite a number of hypotheses. I'm not sure any of them are right. I'll tell you my favorite is that we have independent evidence that Pluto has a global ocean in its interior, an ocean of liquid water ice, and models indicate that it should be slowly freezing over time, with a freezing timescale many times the age of the solar system. So as it freezes, it's releasing latent heat, and the energy budget predictions of that release of latent heat are consistent with causing the very convection that we see. So that's the horse I would bet on. We look across the surface of Pluto and count the craters and map them as a function of location. We see a very different situation than at Charon. Instead of having a uniform population of craters, we find that there are very strong gradients. So there are much younger and there are much older surface units on the surface. There are intermediate aged units as well. And here we're plotting the recovered ages in size frequency diagrams of different surface units. You see some that are 4 billion years old by this isochrone. Some, like Sputnik, that were born yesterday, with an upper limit age of 30 million years and a most likely expectation of about 10 million years or less. But we also find regions like Eastern Tombaugh Regio that are intermediate in age that tell us that Pluto hasn't suddenly become active in the recent past, that it has shown activity across the entire 4 billion years. And this was another geophysical surprise, because it was not expected that small planets with a high ratio of surface area to mass could prevent internal freezing and the extinction of their geologic engine over 4 billion years. This is the first example we have been to of a world this size that was not influenced by large tidal energy inputs in a tug of war in a satellite system with a giant planet. So this we knew would be a test of whether we understood how interiors of small icy planets work or not. And there are basically two theories. You will see activity or you will not. And of course we saw lots of activity, and now we're trying to understand it. I've really told you the science behind this image for the most part. Steep topography means a water ice crust. But I like this image because, first, it's an area about the size of my home state, Colorado, in the United States. And we have the Rocky Mountains, which have very similar altitudes above the surface plane to these mountains out in the Kuiper Belt. And our mountains have snow caps. In fact, I left my house 3 days ago, and it had just snowed. And there's beautiful white frosting across all the peaks of the Rockies made of H2O. We have compositional spectra of this region, and all of these snow caps are made of methane, natural gas, that is condensing at high altitude where it's colder in the atmosphere, and acting in a very similar way that water precipitates out in the Earth's atmosphere. Just fascinating. I only have time to touch on a couple more subjects, so let me be quick. We believe that we found strong evidence for a number of cryovolcanoes on the surface. This one is probably the largest. It's about the size of Mauna Loa in Hawaii, about 150 kilometers in diameter. The central caldera is about 4 kilometers deep. And on the flanks of this feature, we can only find one crater, so we age date it at something like 100 million years old. It's a constructional feature that was built recently. How Pluto maintains this activity, we really can't tell. The other volcanoes that we found on the encounter hemisphere, or volcano candidates, are a little smaller, but they're all in the same region, what we call a volcanic district on Pluto, down here in the south, on the encounter hemisphere. There may be more volcanoes in the polar shadow terrains or the far side, but we don't have the resolution to tell. But even the discovery of a couple is changing our view of Pluto, because we have to now understand not just how the molecular nitrogen can convect, but also how these cryovolcanoes can be powered. This is perhaps the most enigmatic feature on the surface that we found. It's in the mountains called the Aladrisi Mountains up here in the northwest of Sputnik. And stereo imaging shows us that this feature is perfectly flat and lies in a mountain valley. It's made of molecular nitrogen. We have the reflectance spectroscopy to prove it. It looks like a frozen lake, which makes no sense on current day Pluto because we're nowhere near the triple point. Liquids can't exist on the surface of Pluto. They can't pool and they can't run. But across the surface of Pluto, we find this and other lines of evidence for formerly standing or flowing liquids. We believe that we understand what might be causing it. Pluto has Milankovitch cycles like the Earth, but with 10 times greater obliquity amplitude. This caused the insolation pattern on the surface to change, and I published a paper in Icarus this year showing that the pressure cycle variations on this 4 million year frequency in the obliquity cycles can drive the pressure as high as a couple hundred millibars. So much higher than the surface pressure on Mars and above the triple point for liquid nitrogen. So this cryptic or paleo lake, we think is indirect evidence confirming that climate cycle interaction that's been occurring on Pluto's surface for a long time. The last thing that I want to show you is just sort of for fun. It's a high-resolution strip that we imaged. They may have to start it up in the booth. But we're going to fly over the surface of Pluto at an equivalent altitude of about an airplane at about 10 kilometers from the North Pole here down into Sputnik Planitia using the highest resolution images at 70 meters per pixel that New Horizons obtained, again with a panchromatic camera. But you can look into the interiors of craters and see the surface variation there. You can see those linear tracks that may be dust devils from these earlier epochs of higher surface pressure. You can see these mountain ranges and then the big mountain blocks that are chaotically broken up on the margin with Sputnik. And then you can see the cellular pattern and dune fields, we believe. On the surface, wind streaks have been proposed for those features across this featureless, craterless plane of molecular nitrogen called Sputnik. Let me close by saying that we have a fair bit of evidence that the population of dwarf planets in the Kuiper belt is at least as diverse in their physical properties as the terrestrial planets. If you think about how different Venus and Earth and Mars and Mercury all are, the planets of the Kuiper belt have different surface compositions, rotational states, different satellite populations. Some have atmospheres, some do not, and they have a wide disparity in bulk densities. I think that New Horizons has shown that we've only scratched the surface of this third zone of the solar system. And the science beckons for more missions and more exploration back to Pluto with an orbiter for this dynamic world and flybys to reconnoiter the other objects in the Kuiper belt. I will close with this true color image made from the far side of Pluto during the occultations, in which you can see Pluto's atmosphere me-scattering. It's just beautiful, and it was worth the 25 years to get the image. Thank you very much. There's time for questions.
Let's keep very tight time. We'll get in a couple and then the drink afterwards.
Yeah, you're the best.
Thank you so much, Alan. We're pretty much up with the clock, but time for two quick questions at the back there.
Huge congratulations. I think, transformed our understanding certainly of the outer solar system and the solar system as a whole, and has big implications, in my view, for understanding exoplanets and so on. So a fantastic mission. My question is that you talked about those tholins on Charon. So is there any nitrogen in those compounds? And if so, is there any sign that you've got some kind of prebiotic species, chemical species there?
Yeah, there must be some nitrogen there, but we don't see it in the reflectance spectroscopy. And here's why. The nitrogen is, 28 AMUs. The methane is only 16 AMUs. But in Jean's escape, the molecular weight enters the escape rate calculation in the numerator of an exponential. And so it turns out that when you do the math, the nitrogen is escaping 1,000 times more slowly, only about 10 to the 22 per second. So there's very little nitrogen in the mix with the methane, just not enough for us to see. No doubt there is radiation chemistry taking place between carbons and nitrogens and hydrogens and making nitriles, but they must be a minor constituent.
Thank you. I noticed from the picture of Pluto that it was nice and round like you'd expect a planet to be. But the picture of Charon at the top by the red stain, it seemed to be really rather wobbly along the edge. I mean, are there big variations in the radius there? And if so, why?
Okay, good question. First, both objects are in hydrostatic equilibrium.
Yeah.
When we fit a triaxial ellipsoid to each from all the available imagery and light curve data, we can't find any deviation from a spheroid for either object except due to local topography. All right? And so Charon is also mechanically relaxed. That's what I mean by hydrostatic equilibrium. It has a larger variation in surface topography than we see almost anywhere else among the icy satellites. But that's just got to do with the peculiarities of its surface geology, just on the thin rind on the top, the crust of the planet.
Okay, so it is just that variation is basically large mountains.
Large mountains and large holes in the ground. Yeah.
Okay, I'm afraid we do have to finish. I get into big trouble if we run on past 6 o'clock. However, Alan is going across to the RS library for drinks, and I'm sure he'd be happy to speak to anybody on this.
We all know science gets better with drinks.
So can we thank Alan very much indeed.